Okay, good morning, lads and ladies. Welcome back to Calc 2. Yesterday, we spent a little bit more time playing around with use substitution, and then we saw kind of how to find areas between curves a little bit. Today, we're going to keep charging in that direction. We're going to look at a few more area between curves problems, and then I'm going to show you this new thing called average value of a function, which is an important concept for statistics, and it solves a problem that is kind of not obvious, which is like, how do you take a set that has infinite number of data points and find the average of that set. We know if we have finitely many data points, we just add them all up and divide by the number of things. That's pretty easy. But what if you have infinitely many things? That gets a little trickier. Okay. But before we get into any of that, we need to finish up section 6.1. Oh. This is MAC 2312, section 004. That is Calc 2. And today is the 27th of August, 2021. And like I said, the things that we're going to do today finish section 6.1 on areas between curves. And we're going to look at section 6.5, which is on average value. All right, and after we do those things, we will be done. Section 6.1 is an interesting section for a few reasons, mostly because it has you practicing drawing lots of graphs. And that's a skill that you're really going to need in section 6.2 and 6.3, where we'll be finding volumes. It'll also be relevant when we talk about section 7.8 on improper integrals. So while you might feel like the 6.1 problems are a little bit too easy, or even if your Calc 1 class did go over section 6.1, I want you to take those problems seriously. I want to make sure that you're drawing the graphs by hand. I don't have any red here. So when doing the homework here, you must practice graphing, shading by hand. I'm just telling you, if you don't practice that now, it's going to catch you out on the test. There are going to be multiple problems on the test where I say draw a graph and then do blah, 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 blah. And if you don't practice doing that, you're going to get into trouble. So I know WebAssign, it's one of the unfortunate things about WebAssign, right? WebAssign on these graphing problems always just gives you like 4 graphs and says, pick the right one, which is better than nothing. But especially with me giving you guys so many attempts on each problem, it's possible to just spam until you get it. And I know that in desperate moments, plenty of people will do that. I just want to tell you so that it's been said that as you work the homework, you need to draw those graphs by hand. Otherwise, you won't be ready for the test. Okay. Say, recall. Last time we saw kind of 2 big pictures, 2 big ideas. Some color here. I have a function f, some other function g, and specify some interval from a to b, and let's say, okay, find me the area between the functions f and g on the interval a, b, or from x equals a to x equals b. The way you do this the way you're going to come in here and find this area is by integrating the upper function minus the lower function from a to b. So it's going to be a definite integral. So the area between on the interval ab, this is the shaded area above. That's the integral from a to b of f of x, the upper function, minus g of x, the lower function. They integrate the upper minus the lower. Right? And we saw that it doesn't matter if f and g are positive, negative, maybe f is way up here, and maybe g is way down here. Still doesn't matter, because you're looking at like these little Riemann strips or little Riemann rectangles that go from the upper guy down to the lower guy. We also saw that if these curves are not functions of x, i.e. their graphs don't pass the vertical line test, but they do pass the horizontal line test, meaning they do represent x as a function of y. This is the kind of first big thing we saw from 6.1. Like this, x equals f of y g of y. Then our situation is a little bit more like this. F of y is something like this. Yeah, definitely not a function of x, but it is a function of y. And maybe your g of y is something like this. I haven't changed the x and y axes. This is still the x-axis. This is still the y-axis. I've just kind of changed the functions. So now the area that we're after, I specify a kind of the other thing here is that rather than specifying an x interval, here you'll specify a y interval. Y equals a, and over here is y equals b. What we're looking for here would be this one. And that to calculate this area, specify here on the y interval, this would be equal to, it's the same thing, only you integrate the right minus the left instead of the upper minus the lower. So this would be the integral from a to b of f of y minus g of y dy. And a few things worth noting here. Yeah, definitely right minus left. Kind of the analogous concept of an upper minus a lower when you turn your head sideways like that is right minus left. The other thing I'd like to point out here is that these are y values. The bounds of integration, the limits of integration here are y values, not x values. So this is y equals a, this is y equals b. So if you're trying to find the area between two curves, the very first thing you need to do is sketch the curves. And then based on the geometry of the situation, you're going to decide whether your integral will be done with respect to y, which is the second picture, or with respect to x, which is the first picture. Maybe your region is such that you'll want to split it up and do part of it with respect to x and part of it with respect to y. That would be a difficult problem. You're not going to see much stuff like that. But that's the first step. Draw the picture and determine whether you're going to integrate dy, like in the second picture, or integrate dx, like in the first picture. Then you need to figure out the bounds of integration. You know, where are you trying to find the area? Do these functions cross one another? Do they touch somewhere? Does one start out as the upper and then become the lower? If so, you'll need to split the problem up, like the example we saw with sine and cosine at the end of class last time. If not, then you can just straight up integrate upper minus lower or right minus left. Before I look at more explicit examples, the last thing I want to do is add a bit of detail to these pictures. If you're integrating with respect to x, if you have a clear upper and lower function everywhere along your interval, then you should remember that your integral is really like adding up a bunch of teeny tiny rectangles of this form, right? Whose width is delta x and whose height comes from f minus g. And that's why the integral looks the way it does. You've got your height times your width, and you're just integrating it. In the other picture, the reason things come out the way they do, the reason that formula looks the way it does, is because your integral is really adding up infinitely many teeny tiny rectangles that look like this. So the width here is delta x, or sorry, delta y. Delta y, it's a little vertical thickness. And this dimension, we call it the height or whatever, is again f minus g. So that's why the formulas look the way they do. I encourage you, when you draw your pictures, to also draw in the little strip. Because again, in section 6.2 and 6.3, we're going to start rotating regions that look like this. And the key to understanding how to find the volumes of those rotated regions will be to think about what happens to that strip. Okay. So let's look at one or two more examples. Let me pull up something from the textbook. Okay, so this is all that we have seen. This is yes, and easy examples like that are easy. Here's one which we have not done, right? So let's take a look at that. Let's find the area enclosed by solution. Find the area enclosed by y equals x minus 1 and y squared equals 2x plus 6. plus 6 minus 6 plus 6. Okay. So now in the book there, they've sketched the graph for us, so we kind of have an idea of what's going to happen already. But let me show you how you would do this if you didn't know already. Book hadn't provided the picture. The line y equals x minus 1, I know everybody knows how to graph that. So I want to start by thinking about the parabola. Since this is a quadratic where the y is squared, not the x, you know it's going to be a parabola which opens sideways, either to the left or to the right. And then the easiest way to get a good sketch of this is going to be to solve it for x. So this is 1/2 times y squared minus 6 equals x. All right, so here's one of your functions. This is like f of y or g of y. If you imagine graphing this, imagine I just gave you 1/2 times x squared minus 6. Everybody knows what to do with that, right? That's like x squared, but shifted down 6 units and then kind of widened out by a factor of 2. Well, this is the same thing. It's just sideways, right? So you turn your head sideways and do the same thing. Instead of shifting down 6, how should I say this? Yeah, instead of shifting down 6 units, you would shift left. And instead of widening out like this, you're going to widen out like this. You can also plot some points, and I think that's wise. So let's do that. When y is equal to 0, what do we get? We get 1/2 times 0 squared minus 6 equals x, which is the same as saying x equals -3. So the point -3, 0 is on the graph, and that's actually going to be your vertex, right? Another way to say this, you can put this into vertex form. So let me just 1, 3. All right, so my vertex is here. Since the y squared is positive, this is like 1/2 y squared minus 3. That would be the vertex form. The coefficient of y squared is positive. That means we're going to open to the right because this is the increasing or positive x direction. The other things you might want are like what we normally call the x-intercepts for a parabola that opens up and down. Here there would be y-intercepts, and you get that by looking at what happens when x is equal to 0. Then we have 1/2 times y squared minus 6 equals 0, which means y is equal to plus and minus the square root of 6. Now, how big is the square root of 6? Well, 2 squared is 4, 3 squared is 9. So the square root of 6 has to be a little bit bigger than 2, considerably smaller than 3. And that sort of estimate is good enough for us. Bigger than 2, smaller than 3, somewhere like right here. Right here, something like that. So, oh shit, I should use color here. Let me use using blue for the left function before, right? So here's that first curve. And my spacing here isn't quite symmetric, but that point. So here's negative square root of 6. Here's positive square root.
On the exam, do you want us to like give you exact points of the x and y intercept, or can we just draw it and you could just have like an estimate on what it looks like?
I'm going to give you very specific rules on each question. Like I'll say, graph these functions, plot at least 3 points explicitly, or graph these functions, plot at least 2 points explicitly. I would say that the fastest way to get a graph of something like this that you can be confident about is by plotting a few points. It's not hard to find the x and y intercepts here, right? It's pretty easy. So I think it's a good thing to get in the habit of. But the exam problems generally won't explicitly require intercepts. They will generally require a certain number of points plotted explicitly though. So, you know, I could say, give me any 3 points. They don't necessarily have to be the intercepts. All right. So this is our first function. It's this guy. And if I wanted to write that in the notation that we've been using, g of y, this is x equals g of y. So g of y here is, I'll distribute the 1/2. This is 1/2 y squared minus 3. The other curve, y equals x minus 1, you know how to graph that already. That's going to look something like this, right? That's a line with slope 1 and y-intercept -1. Everybody's known how to graph that for years. But I'd like to put that in this form also, right? So if you solve y equals x minus 1 for x, you get y plus 1 equals x. So the f of y here is y plus 1. And now that you have your picture, you can tell what they're talking about by the area enclosed here. They didn't specify an interval, right? They didn't say find the area bounded between these functions from y equals 2 to y equals 7. They just said find the area enclosed. So it's not exactly in the way that that our theorems there or our formulas tell us how to work. But once you have this picture, you can see how to apply the formula. Got to draw your picture first. And now I see, okay, this is the area I'm going after. I'm looking for this stuff. I know what my right function is. That's f of y equals y plus 1. I know what my left function is. That's g of y equals 1/2 y squared minus 3. And I know I could subtract those and integrate. That's not hard. Those are power rule integrals, easy peasy, lemon squeezy. What do I not have that I need?
The like
Bounds.
yeah, bounds.
Yeah, I don't know the bounds. I don't know. I'm integrating from where to where. So I need the two y values that serve as the start and the stop of this region. And those are the y values of the points I've just put up here. So I need to know what's the y value here and what's the y value here. I'm going to integrate from y equals this up to y equals this. And again, you can draw on your little strips here. The strip can go wherever you want. Since these are definitely functions of y, or at least the parabola is definitely a function of y, not a function of x. I know my strip has to go oriented like this, side to side. I know its thickness is a little dy thickness. And I know that the length of this strip, the thing I'm going to integrate, is the purple function minus the blue function, or f minus g. But I got to find those intersection points. So we know that the shaded area equals integral y equals a to y equals b f of y minus g of y, right? The right minus the left, dy, which is the integral from a to b of y plus 1 minus 1/2 y squared minus 3 dy, but we don't yet know a and b. And these numbers, a and b, These are the y coordinate of the intersection points. So we got to find those intersection points. How do we find the points where two curves meet? How does one do that?
Set the equations equal to each other.
Very good, very good. And we know we're looking for y values, so we just set this equal to this and solve for y. Okay, so that's what I'll do here. That means I'm setting y plus 1 equal to 1/2 y squared minus 3. We can multiply everything by 2 if we want, and we can pull everything to one side. So this is going to look like 0 equals y squared minus 2y. And then I would have minus 6 from this and minus 2 when I pull this over. So that's minus 8. And then let's see, we see whose factors. So can we come up with two numbers whose product is -8 and whose sum is -2, -4, +2? All right. So y equals -2 and y equals +4. That's it. So this guy right down here, these guys actually meet right at -2. And up here, these guys actually meet right at 4. Notice that my integral here is equal to the integral from -2 to +4. I can combine like terms and whatnot in here. I'll have -1/2 y squared plus y, and then +1 minus -3 plus 4. And this integral is being done dy. Right, I think that's all the hard stuff in this problem. I think that's all the things that are conceptually challenging, or you might have a difficult time figuring out what to do. I am going to finish it. We'll evaluate this integral, but I want to pause for a moment, give you a chance to get your notes caught up, make sure your picture is nice, and then ask any questions you have. While you're polishing the notes, I will refill my coffee. All right. So is there anything we'd like to ask or look more closely at regarding this setup here? Everything that leads us to that integral. Okay then. As with any definite integral, we need to calculate an antiderivative and then evaluate that antiderivative between some bounds. Antiderivative of -1/2 y squared is -2 1/6 y cubed. I'm just increasing the power by 1, so the 2 becomes a 3. And then you divide by that new power. When I divide -1/2 by 3, I get -1/6. Plus integral of y is 1/2 y squared. And the integral of 4 is 4y. And this gets evaluated from -2 up to +4. And now we just have some arithmetic to do. So when I plug in the 4, I'll combine these terms. So it's going to be -4 cubed over 6 plus 4 squared over 2 plus 4 times 4. And then I'll subtract from that what I get when I plug in -2, which is going to be -2 cubed over 6 plus -2 squared over 2 plus 4 times -2. One of the things you need to do in this class is just become very methodical, right? Have a system that you follow and follow it carefully all the time. This is the notation I like for evaluation because the brackets kind of remind me that I can factor things out, constants. That this evaluation thing really is like a linear function of the stuff inside. Split it up if you wanted all of that. So this is how I like to write those evaluations. If you have another notation you like, feel free to use it. 4 cubed is 64. 4 squared is 16. 4 times 4 is also 16. This first piece is -64/6 plus this is 16 over 2, which is 8 plus 4 times 4, which is 16. Leave the brackets here at this step. Minus, and then let's clean everything up inside over here. -2 cubed is -8. -8 is +8, so that's an 8/6. -2 squared is +4. +4 divided by 2 is just 2. And then 4 times -2 is negative. Okay, so I have 2 ratios over 6, and then I have a bunch of integers. 8 plus 16 is 24. 2 minus 8 is -6. That's 24 minus -6. 24 plus 6, which is 30. That's the integer part. And then I have minus 64/6 minus 8/6. So -64 minus 8 is -72. So -72/6 from the fractions. And then I do think 72 is divisible by 6. What is 72 divided by 6? 24? Is that right? 72. I'm thinking feet, right? Isn't 72 inches 6 feet? So this would be 12, not 20. So we've got 30 minus 12. Which is 20 minus 2 is 18. And that's it. Any questions on the calculus steps here?
I have a question on the answer, Professor.
I can hear you very faintly.
I'm gonna try to yell a little bit to see if you can hear me. What would be the unit for that for the answer at the end? Would it be like meters squared or something?
It's a good question. So here they didn't tell us what we're measuring length in, right? So like when I say that, you know, this is like x equals 3, does that mean this distance is 3 meters or 3 inches or 3 yards? So the problem was given unitless, So what we would do is we'd say, if this is, if I consider 1 unit of length here just to be 1 unit, then I would say this is in square units. If
Um,
unit of length in the graph was 1 meter, then this would be meters squared. If 1 unit of length in the graph was 1 inch, then this would be square inches. But since they didn't specify units for the graph, then it's just square units. Does that make sense?
Thank you.
also on the top right, when you set the x equal to 0, you have 1/2 parentheses y squared minus 6. Shouldn't y equal plus or minus the square root of 3?
Nah,
Wait.
try it out. So if you distribute the 1/2, then you get 1/2 y squared minus 6.
Yeah, and
Sorry,
then
1/2 y squared minus 3. Then you add the 3 over, and then you multiply by 2, and then you take square roots.
okay.
Easier way to see it is just factor this as a difference of squares. Y squared minus 6 is y minus root 6 times y plus root 6. The 1/2, because it's all the way out, doesn't have any effect on the solutions to that equation.
Okay.
Good thought. Other questions or concerns here?
Also, where you divide 77 by 6 is 12.8. Do you want us to keep like 13 or 12?
No, this is a 72.
72?
Yeah.
All right.
Sorry, my bad handwriting there, isn't it? That's a 72.
All right. Sorry about that.
That's what it should be, right? Yeah, 64 plus 8. Yeah. Okay. All right. Anything else that we're wondering about here? Okay. Let's take a look at maybe just one more kind of tricky example. Let's do something where we don't have a solution or a graph provided to us. That can be fun. Did a nice tricky example last time. Let's take a look at looks like fun. What you guys pick? Do you want to see 24, 25? Any strong feelings? You can let me know in the chat or just shout out.
24.
24. All right. So let's find the area enclosed by y equals cos x and y equals 1 minus cos x from 0 to pi. Okay. So again, the trick is just sketching a decent graph of these two functions. Let's start with cos x. I'll mark this as 2 pi, which makes halfway there. Over 2 and 3 pi over 2. You know, the cosine of 0 is 1. The cosine of pi over 2 is 0. The cosine of pi is -1. cosine of 3 pi over 2 is 0, and the cosine of 2 pi is back to 1. You've got tangents looking like these. Maybe I'll do this graph in blue. All right, so there's good old-fashioned cosine. And then 1 minus cos x. That's actually, let's see. Room for this. I may have to redraw this picture in just a second. So how do you get the graph of 1 minus cos x from the graph of cos x? Well, you flip cosine over vertically, and then you shift everything up by 1. So your sort of new equilibrium here, this is the way I like to draw this, and I'll probably redraw this in just a minute, so we have a little bit more space to play with. I'm going to kind of treat this dotted line as my new equilibrium, or like horizontal axis. And I'm going to draw a flipped over cosine. So that means I start out down from equilibrium by 1. I go through the equilibrium at pi over 2, and then I'll go up as high as 2 when we get to pi. And then I come down through the equilibrium again at 3 pi over 2, and I come back to 0. So this guy's going to have tangents looking like this. I'll drop in purple. So of course, both functions kind of continue on doing their thing forever and ever, amen. But I'm only interested in what's going on from 0 to pi. Looks like we do have enough room here, so I'll go ahead and work with this graph. I'll leave this as my main graph. This guy is y equals 1 minus cos x. And this guy is y equals cos x himself. Now, if you had a hard time following what I did there to get those graphs, specifically the graph of 1 minus cos x, I want to strongly encourage you check out Paul's online notes, graphs of trig functions. It's in the algebra review. If you go to the modules in our class, go to the review material modules. It's one of the top things right here, right? Algebra trig review from Paul's online notes. It's right here. You can look at the graphs of trig functions. He shows you how to graph lots of stuff, starting with the basic trig functions. And if you move to the next section, he should show you how to do, oh no, trig identities. All right. I guess you have to remember your transformation rules. I'll try to find something else. Let me see. I'll add something here. The modules there. These transformed trig function graphs, if you forget. But the area we're looking from 0 to pi. Let me draw a line in here at pi. And I'm looking for the area that's between these two curves. So from 0 to whatever this point is, the blue function is on top. So that's the little area enclosed by them. And then from whatever that x value is, all the way up to pi, the purple function is on top. So here we're looking at this region. All right, so these are the the areas we're trying to find. And we really do have to think of it as two different regions. Because the one function is on top, cos x is on top from here to here, and 1 minus cos x is on top from here to here. So we'll have to calculate those as separate integrals. We need to find this guy. All right. So the shaded area is equal to the integral from 0 to question mark of the blue minus the purple, which is cos x minus 1 minus cos x dx plus the integral from question mark to pi of purple minus blue, which is 1 minus cos x minus cos x dx. And in each of these regions, or maybe just in one, you could draw in your little strip. Doesn't have to be perfect. So you see that in the second region, the height of that strip is given by the purple minus the blue. That's why this second integral is 1 minus cos x minus cos x, purple minus blue. How do I find the question mark? Right, this is the bit of information that I need in order to proceed. How do I find this guy?
Set them equal to each other.
Yep, just like before. So you set cos x equal to 1 minus cos x and solve for x.
How do you know what the shaded area is? Like, shouldn't it be the whole space in the middle and the little part on the right side too? Or
Well, they said we're only looking from 0 to pi.
oh, okay.
So the problem was kind enough to specify here that we're just working from 0 to pi. But if they didn't, yeah, I mean, then we would have a real problem on our hands, right? There's infinitely many regions that they enclose. But I'm glad that you asked that question because it also kind of hints at another thing, like how do I know I'm not looking for this area down here or this area up here? We're always looking for a region that's actually enclosed, that has a clear boundary. But even with that in mind, unless they told us this, we would have a problem. All right, let's solve this. This is equivalent to 2 cos x equals 1, which is itself equivalent to cos x equals 1/2. And there's infinitely many solutions to this equation, right? And there's infinitely many intersection points. There's another intersection point over here. There's the one here that we're looking for. There's another one here. There's another one here. These two graphs touch infinitely many times. And each one of those touches is a solution to this equation. How do I know which solution to take?
You make sure it's between the
Positive.
bounds you're given.
Yeah, very good. I like Juan's answer. We got to make sure that that solution comes from the interval 0 to pi. I know I'm only interested in what's going on from here to here. And between 0 and pi, these only touch once. Another way of saying that is we're looking for the smallest positive solution. We can see that from the graph, right? This is the first x value where they touch. So let me go ahead and just write down all the solutions to this equation really fast. We haven't solved the trig equation together yet. I'll remind you how we do that. I'm looking for all the points on the unit circle where the x coordinate is equal to positive 1/2. So that's this guy up here, and also his symmetric brother down there. This is pi over 3. And I could call this negative pi over 3 if I wanted. Or I could measure it around like this as 7 pi over 3. So our solutions, sorry, not 7 pi over 3, 5 pi over 3, right? 1, 2, 3, 4, 5 pi over 3. Solutions are x equals pi over 3 plus 2k pi, and x equals 5 pi over 3 plus 2k pi, where k is allowed to be any integer. Right, so if we needed all those solutions, this is how you write them down. But again, we're just looking for the first positive solution, which is pi over 3. Because that's the only one that falls between 0 and pi, or if you prefer, it's the smallest one, which is positive. So our area is equal to the integral from 0 to pi over 3 of cos x minus 1 minus cos x. That's 2 cos x minus 1 dx plus the integral from pi over 3 to pi of 1 minus cos x minus cos x. That's 1 minus 2 cos x dx. Antiderivatives for each of these are fairly simple. Antiderivative for cosine is positive sine, right? Because the derivative of sine is cosine. So this is 2 sine x minus antiderivative for 1 is x. We evaluate that from 0 to pi over 3. And then we use the same antiderivative rules here. The 1 integrates to x, the minus 2 cos x integrates to minus 2 sine of x, and we evaluate this from pi over 3 to plugging in the bounds. When I plug in pi over 3 here, I get 2 times the sine of pi over 3. What is the sine of pi over 3?
Is it root 3 over 2?
Very good. Square root of 3 over 3. Minus x, which is pi over 3. And when I plug in 0 here, I get 2 times the sine of 0 minus 0. What is the sine of 0?
Zero.
0. Very good. You got to know that unit circle. These need to be coming fast and quick, guys. So no reason to hesitate here. Please shut up. When I plug in pi in the second piece, so the lower bound gives me nothing from the first piece, right? 2 times 0 minus 0, that's 0. So everything in that first piece comes from the upper bound. This is done. This is equal to this. This guy, when I plug in pi, I get pi minus 2 times the sine of pi. What's the sine of pi?
0.
0. Very good. When I plug in pi over 3, so I've got this minus, I'll open up parentheses here. When I subtract and plug in the pi over 3, I'll have pi over 3 minus 2 times, again, the sine of pi over 3 is the square root of 3, 2. Right. So that's all the evaluation done. Yeah, I could shade this a little bit more. So we've kind of got these 2 separate spots. There's this big one and this little one over here.
Could you explain that last part again?
I'm sorry,
Could you explain that last part again? The one like down there.
the second evaluation piece? Yeah, sure. So
Yeah.
when I plug in pi, I get pi minus 2 times the sine of pi, which is pi minus 2 times 0, which is just pi. So this is what I get when I plug in pi to this whole thing. And this is what I get when I plug in pi over 3 to this whole thing. Pi over 3 minus 2 times the sine of pi over 3. So I think this part you can probably see pretty well, right? The parentheses here are what you get when you plug in pi over 3. The pi is what you get when you plug in pi. It's just that the sine of pi is 0. And then something
Perfect.
over here. So when you plug in pi over 3, you get 2 times the sine of pi over 3, which is 2 times root 3 over 2, minus pi over 3. So this is what you get when you plug in pi over 3. And when you plug in 0 to this expression, everything is 0. So there's like a minus 0 in here that I'm not writing. 0.
Thank you.
Of course. All right, so now we just want to clean this up. This is the square root of 3 minus pi over 3 plus pi minus pi over 3. And then the minus minus here is going to make plus the square root of 3. So altogether, I've got 2 square roots of 3. I've got minus pi over 3 minus pi over 3, which is minus 2 pi over 3, and then plus pi. Pi is 3 pi over 3. So minus 2 pi over 3 plus 3 pi over 3 is plus 1 pi. All right, again, I'll give you a second to take a look at your notes, make sure everything is comfy, cozy, clear, and ask any questions. Okay, then that's areas between curves. You'll find some of the problems you need to split up, some of them you don't. Some of the problems you'll integrate with respect to y, some of them you'll integrate with respect to x. Everything comes from the picture, so just practice drawing the pictures. The graphing skills need to develop. The last thing we're going to talk about today is this concept of average value. So let's do it. You know that to find the average of, a finite set of values like y1, y2, up to yn. So if I have like n numbers here, y1, y2, all the way up to yn, the way I find the average of those is by computing. In statistics, you would usually call it something like y bar. But you add them all up, right? You add up all the things, you add up all the numbers, and then you divide by the number of numbers. So the way you average 2 things is to add them up and divide by 2. The way you average 3 things is to add them up and divide by 3. The way you average n numbers is to add them up and divide by n. But what if you want to average all the outputs from a function y equals f of x from, say, x equals a to x equals b. That's the idea. And it turns out a very important idea in statistics. Also is surprisingly important in some engineering and physics fields. How many outputs are there from this function between a and b, just in general?
Infinite.
Yeah, infinitely many, right? Like there could be a different output for every real number between a and b. And there's a shitload of real numbers between a and b. As long as a and b are distinct, there's infinitely many real numbers between them. It's not even a small infinity, it's like a big infinity. So this is a problem. But what I could do is take a sampling. Maybe a is over here, and b is over here. I could chop up my interval into subintervals, right? And then just average the associated y values. And you can probably smell where this is going. In place of a sum like this, you're going to have an integral. So if we chop up the interval a, b, and average a sample of points, a sampling of outputs, we get, well, this point right here, this would be, the y value here would be f of a, and we call a x0, and then this would be x1 and x2, and I'll call b here xn. Then the average of those, let me call this x1, and then this x2, and then this x3. That way I have n terms instead of n plus 1 terms. That'll be nicer. Then what we have here is f of x1 plus f of x2 plus out to f of xn. And I want to average that. So I'm going to divide by the number of terms here. There's n terms here. Well, this is the same as 1 over n times sigma I from 1 to n f of xi, which is the same as sigma I from 1 to n f of xi times 1 over n. Right, this would be like our average, and this is an integral. So this switch is a Riemann sum for the integral. You can think of this as your like y value, your f of x, and this is like your delta x or your dx. So this is a Riemann sum for the integral from a to b, f of x dx. So the integral plays the role of like adding up all the y values. I'll show you how your book, they have some nice pictures here. Doing the same thing, we take some sample points, right? But then the trick is, let me say this. So 1 over n is not your delta x unless you have a b minus a, right? Remember that delta x is always b minus a over n. So let me take this one line further here and say this is like 1 over b minus a times the integral from, or the sum from I equals 1 to n, f of xi times delta x. So delta x is the width between any two things here, which is b minus a, all divided by n, because I'm equally spaced sample points. So really that's a Riemann sum for this guy. Which is, because 1 over b minus a is a constant, you get that. And this is what we call the average value. It's the average value for the function f on the interval a, b. We just try to add up all these y values and then divide by the number of terms. That's this. You can rewrite that in sigma notation like this. Then you pull the 1 over n inside and multiply by b minus a over b minus a. Then I take the 1 over n and the b minus a from upstairs. I combine those into b minus a over n. That's your delta x. And the copy of b minus a from downstairs, I bring that out from. So you end up with this guy, which is a Riemann sum for this integral. So this integral is the average value of that function, right? As n goes to infinity, this sampling becomes a true average, and the Riemann sum becomes an integral. There are some nice ways of interpreting this geometrically, especially when you think about the mean value theorem. Here it is, your mean value theorem for integrals. We can say, let me try to convince you over here. So on the one hand, this is very useful for finding things like balancing points, right? If you think of that area under the curve as having some like density, some weight, these are like probability density functions almost. It can help you find a balancing point, which is very important in statistics. It also has a neat interpretation through the mean value theorem. So I'll draw for you this picture. The average value is the unique constant function which encloses the same area as f itself over the interval AB. That's my favorite way to think of this. And then as a consequence of the mean value theorem, that unique constant function, which is the average value, also has to touch the graph of the original function somewhere on AB. So here's the graph of f of x. Let me try to estimate this. Something like that, I think is about right. So the blue function I'm drawing in now, this is the graph of a constant function. I think you would all agree, right? It's a horizontal line. This is the graph of the constant function f ad, right? The average value is just a number. So when you think of it as a function, it's a constant function. Your y-axis, this is your x-axis. And the cool thing is that the area enclosed by the blue function from A to B is the same as the area enclosed by the original. But the blue function is a constant function. So that's a pretty sneaky trick. Okay. So the blue shaded area is actually equal to the pencil shaded area. This is one very clever way of defining the average value. You could say that the average value for a function is the unique constant function that encloses the same area as the original function on the interval AB. One last cool thing.
Professor, what happens with all the values that are not enclosed by both f of x and f average, like that little sliver right on top?
So kind of this piece right here.
No, I'm talking about that, yeah, right there.
Yeah, so this piece is enclosed by the average value, but not by the original. This piece is enclosed by the original, but not the average value. So one way to think of it is the amount of shit up here has the same area as the shit down here, because they have to kind of balance each other out. Because we know that the pencil shaded area has to be equal to the blue shaded area. Anything covered by the blue and not by the pencil has to be equal in size to anything covered by the pencil and not the blue. So it also does this kind of cool bifurcation thing. If your function is monotone on the interval AB, it has this neat way of finding a point where you can split into two equally weighted parts. That's kind of related to this concept of a balance point that I mentioned a minute ago from statistics.
Perfect, thank you.
It's very cool. The last thing I'll say here, so first let me write this down, get the words up here. So the average value f av for a function f of x on interval AB is the unique constant function which encloses the same area as f of x on the interval. And then the last kind of cool thing in here is the relationship with the mean value theorem for integrals. So in purple, I've added a label for the number where the blue hits the black. The mean value theorem for integrals. Let me remind you the original mean value theorem. This has lots of hypotheses and it's a little bit wonky, but it says if f is continuous on AB, closed AB, and differentiable on the open interval AB, then for some C between A and B, f primed of C will be equal to the slope of the secant line, f of B minus f of A over B minus A. This is the version of the mean value theorem that you learned back in Calc 1. All right, if you have a continuous and differentiable function, then you can draw the secant line, and then guaranteed somewhere in between there, there will be a tangent line which is parallel. The mean value theorem for integrals is nice because it has fewer stipulations. It says if f is continuous on AB, I no longer need f to be differentiable. If f is continuous on AB, then its antiderivative will automatically be differentiable. Then there is a number c between A and B such that, just the same notation your textbook does here, yeah. F of C, such that f of C is equal to f of 1 over b minus a times the integral from a to b f of x dx. Value. So it says that the blue and the black have to touch somewhere between A and B, right? That's this guy.
Professor, can you lower the paper a little bit? Thank you. Also, for the mean value theorem, your first definition, not the one for integrals, after and differentiable on the parentheses, what's inside the parentheses?
Sorry, that's the open interval from A to B.
Thank you.
So if you're differential, or if you're continuous on the closed interval, differentiable on the open interval, then somewhere in between, you have a tangent line that's parallel to your secant line. That's what this is, right? This is the slope of the tangent line at C, and this is the slope of the secant line from A to B. You can kind of see how this piece is similar to this piece. Like if you were to somehow differentiate through this with respect to C, or if you were to kind of replace some of these constants by variables, differentiate and then plug in C, over here you have an f of C, where over here you have an f prime. You've got a 1 over b minus a, you've got a 1 over b minus a. And then if you were to actually evaluate this integral using the fundamental theorem of calculus, that would be capital F of b minus capital F of a, where capital F is an antiderivative for little f, right? So this is like big F of b minus big F of a over b minus a. And this guy over here is the derivative of big F, which is little f. So they're equivalent statements, but the mean value theorem for integral has this other different geometric interpretation that doesn't have anything to do with slopes or being parallel. So it's a fun thing to discuss. And it would be a good practice. Try to prove one from the other. They're equivalent statements. I'll give you a hint here. Let big F of x be an antiderivative for little f of x in the mean value theorem for integrals. And pretty quickly, you should be able to prove the second one from the first. All right, once you see how to do that, I think you'll be able to prove the first from the second similarly without too much trouble. So that's really it. Average value is nifty, but I don't think the problems are going to like rock your world or anything, because it's really just like compute the average value of this function. Okay, we'll just do the integral. So it's more practice with basic integrals. All the problems that I've given you guys are things like this. You know, here's a function, here's an interval, find the average value. I just want you to practice integration. Some of them are going to be U sub problems, like number 5 here. This would definitely be a U sub, but nothing new, nothing crazy. What I really want to show you is just that picture from this section. I want you to try and internalize this idea of like weights, balance points. same areas. Alrighty, so that's it
Can you-
for you guys this week. Any questions before I let you go?
Can you lower the paper just a little bit to see the hint that you wrote right there?
Yeah, of course. It starts here. I do see there's something in the chat also. The class video canvas. Yeah, of course. So the videos from our 2 previous lectures are already up, and as soon as I can, I'll get the video from today up. I have another class to teach right after this, so I can't be processing that video because the computer fan is very loud while I'm teaching that class. But once I finish teaching for the day, I will upload this video.
Thank you, Professor.
Yeah, of course. All right, guys, I got to get running.
Thank you.
See you all on Monday. Next week, we're going to start talking about volumes for solids of revolution. So if you want to read ahead, check out section 6.2. That is it. See you Monday.
Thank you.